I want to start with a few disclaimers. The first is that I landed in France a couple hours ago, so my goal is to just not fall asleep in the next 2 hours and to not say anything totally delusional. I know this is the one that is being recorded. I apologize to those of you on the internet watching this in a couple months from now. The other one that I always like to give is that I do have a minor speech impairment, and so I might pause sometimes during the talk, but I'm here. I haven't fallen asleep. Normally today, who knows, but hopefully not. So yes, so we're going to be talking in my portion of this school about privacy, and how that integrates well with machine learning. We're going to be talking today about just the privacy part, and then we'll talk in future days this week about the machine learning part. And you might wonder, why do we even need privacy in machine learning? If we learn on a big enough database, it should be fine. In this example, if you can see it in the back, is XKCD about why we do need privacy. In case you can't see it, this is a person trying to do autocomplete, and they say, "Long live the revolution. Our next meeting will be at," and then it auto-completes at the docks at midnight on June 28th. So yes, it is true that you're learning a large, complicated model on a large, rich database, but still sometimes you can extract information that perhaps shouldn't be extracted. And this, of course, is a comic and a joke, but these things do happen in practice. So just as an overview, we're going to be talking in these 2 hours, including a break, of course, about some privacy basics. We're going to talk about why do we need privacy? Why can't we just anonymize data and be done with it? And then we'll talk about the formal privacy definition and some properties, and then we'll get into some of the core algorithms that we use. And I want to give a little bit more of a disclaimer, which is that I feel like these 2 hours are kind of like the scene Karate Kid. He waxes the car and paints the fence, and he's like, "This is so boring. It's so easy. How we do interesting stuff?" And then it turns out he was secretly doing that the entire time. And I say that particularly because 4 is going to be very simple, and I don't want you to think that's all, but in fact we have to have this kind of basic foundational core so that we can build upon it and do more exciting, complicated machine learning. And then on Thursday and Friday we'll talk about actual machine learning stuff. So let's start by talking about privacy. What is privacy? And we can say privacy is good. I don't want stalkers peeking in the windows of my house. I don't want overly targeted ads. What do we actually mean computationally when I say I want privacy? And you might say privacy is about protecting identity. And so in this case, I would say if I'm going to do some analysis on some data set containing Alice's information, I don't want to be able to see which line in the database comes from Alice. It's reasonable. And if you do this legally, this comes down to distinguishing between that which can be identifiable and that which cannot, especially in the US laws. This is a very common division. And this is a long quote taken from the former Facebook chief a privacy officer, and he says there's a critical distinction, have a laser, critical distinction between information that can be personally identifiable and those that are not. And so if you believe this, then this just gives you standards, and you can have government bodies in the US things like NIST gives standards about how to treat PII. Over here we have GDPR, and in the 2 hours I've been here, I've gotten a million pop-ups, accept cookies, decline cookies. And so I feel like it's like, every day very real here. And so then if you have standards, then this just leads to like a compliance. And so then you're saying there exist laws, I have to comply with the laws, and then privacy is done. And so this was a Google search from a few years ago, and it like immediately popped up. We do not share PII, and there was about like a 16 million results. I'm sure if I tried it again today, you would find more. And in some sense, this is like not interesting because we can't do like algorithms about this, and this is a question for like lawyers arguing over what is PII and what isn't. But then also from a kind of information theoretic perspective, how do you know what types of information can be identified? And this leads to kind of my favorite tale of like a privacy gone wrong. This was back in 2006. AOL published a kind of like anonymized database of about like 10% of their users and their search history. And so it didn't take long for a New York Times reporter to think this was interesting and just look at the database and see there was a person who had searched for like a landscapes in a certain town, several people with the same last name, and then also like homes sold in like a very specific geographical region. And so like it's not hard to find who that person is. In fact, it was this lady, and she very kindly agreed to be featured in like an article about her search history. I imagine not all of us would. And she searched for some more embarrassing things, like some health ailments, elderly dating sites, and like a dog that pees on things. And apparently this is the dog. And she claimed in her health thing she was searching for a friend. But I bet that she feels her privacy was not protected via compliance with the law. And of course, if you think about your own searches online, you probably search for things in your neighborhood, restaurants, this school, weather, things for your classes, certain papers. Maybe you search for yourself. And so it's not hard to kind of piece together who you are from your search history. And you can't really write down, enumerate, if I remove this from your data record, I can't find out who you are. Or perhaps if I do, I'm going to remove so much content that it isn't data anymore, and it's only noise. And this is the kind of essence of a quote, Cynthia Dwork, who is a prominent privacy researcher who will appear a lot in my talks this week, famously said, de-identified data isn't. Meaning that either it has not been properly de-identified, as in this case, or if you do, you have basically removed the entire content and it's no longer data, it's just noise. So this brings us back to our failed attempt at defining privacy. And so if I define it that way, I'm not really getting at the problem that we're trying to address. Maybe instead, privacy is about promising people freedom from harm. I promise nothing bad is going to happen to you as a result of I'm sharing your data in a particular analysis. That seems like privacy. And so then I might try to formalize that, and I will say some certain analysis is private if it is the case that I know more about Alice afterwards than I did before. And so again, this seems reasonable. I'm not trying to learn about you as an individual. However, there's one fatal flaw here, which is that in fact, it's impossible to achieve this and still learn at the same time. So for example, if there was an insurance company studying a link between a smoking and lung cancer, that's a thing that we want to identify. And if I know Alice smoked, and I then conduct like entire study, I will have learned something about her. So I'm not quite meeting our like attempt to like privacy. However, this is weird because in some sense, this like privacy violation could occur even if I never saw her data. So maybe it's not fair to say this is a privacy violation. And in fact, I want to change how I define privacy so that I don't count this as a violation. The one final attempt is I'm going to add like a text in red, and I'll say, we're still trying to promise people freedom from harm as a result of sharing data. But now like I'm going to say, the analysis is private. If it is the case, the analyst will almost know more about Alice afterwards than they would have if they had done the same analysis on like a database without her data. So we're effectively comparing two worlds, one with you and one without you. And we're saying, if I can learn the same thing in these two worlds, I'm not really learning about you, but I'm learning about the population, and that is our goal of doing machine learning. So in pictures, say that I have some particular database D, and I plug that into my favorite randomized algorithm. It's important that it be randomized, and we'll see why in some number of slides. And so I plug that into my favorite randomized algorithm, and it will get out like a PDF of the kind of like a possible outputs of this algorithm when I use like this input. And I'm now going to imagine if I change Alice into Javier, and I then plug in like this new database that is like the same, except for one person's data, into my same algorithm, I'm going to get out a different curve. And the hope now is that our curve is going to be close. And then we're not going to see like too much of a change. And by close, I actually mean we're going to have like the ratio between these two curves bounded point-wise. And you might think that's a very weird way of like defining privacy, and you'd be right. However, imagine if an adversary observed this output, and they were trying to make inferences about kind of like whose data caused this. Was it Alice? Was it Javier? Well, then they're like a posterior belief is going to be about the same up to this bound on the ratio. And so that's sort of where this like a privacy comes in, is we're going to say like a conditioned on like observing the output, taking a specific value, I cannot make any inferences about the inputs beyond the amount allowed by my like privacy. In math, it says that we'll say some algorithm M that maps from an n tuple of types. And so think of this as being kind of like a database holding n people's data into some arbitrary output range R is going to be parameterized epsilon delta differential private. That is the case. For all pairs of databases that are neighboring, meaning that they're the same except for one person's data, and for all possible things I may produce as a result of this analysis, I'm going to produce that thing with about the same probability under these two different neighboring databases. And I forgot to say this was like originally defined back in like 2006 by like Dwork, McSherry, and Isima. And so effectively, this is bounding the kind of like maximum amount one person's data can change the result of an analysis. And this maximum amount is not in terms of some kind of like additive error, but rather it's based on this kind of like a closeness in the distribution over outputs when I instantiate an algorithm on this input. And also, if you have any questions, please ask. Like I feel like this is a conceptual thing at this point, and we haven't even gotten to that yet. And so effectively, like a differential privacy is kind of like addressing a paradox of being able to learn approximately nothing about an individual while still like enabling meaningful information about the population. And this approximately that I inserted here comes from these from these two parameters, epsilon, delta. And so you can't learn more than what is allowed by these parameters about the individual, and you can still learn a whole lot about the population. Question, yeah. Let me give you a different example. Yeah, because so we will get into this, I think, like at the very end of my period of talks. But it's hard to do differential privacy when you're looking at like producing data. But it's easy to do it when you're doing kind of like an overall analysis. And so for the example, finding a causal link between smoking and lung cancer, I might say, so this S is going to be like, yes, no, is there correlation? We're going to say, I would be just as likely to like output yes if I had your data or if I didn't. Which is true if you're doing meaningful statistics on a kind of like a large enough sample. And this is, I think, why privacy and machine learning actually go hand in hand. Is in fact because of this line, is we're not trying to learn about the individual, we're trying to learn about the population. That's also what is like the point of machine learning, right? It's like you're not trying to learn about your sample or about a specific outlier. You're trying to learn about the population. And so in some sense, this point is kind of key to this connection, and that like a differential privacy inherently constrains you to do the thing that you want to do in machine learning anyway. Mm-hmm. Yes, exactly. And so this is this line here, but this is a definition and not a particular algorithm, not a particular guarantee. And like it is true once we get into privacy accuracy trade-offs, then you're going to have n play a role. Yeah. And it's actually a three-way trade-off of privacy accuracy in your sample. So that's in and handful of time. So we're going to talk about the definition for a little bit more and then have a break and then talk about some kind of algorithms to achieve this. Because I think in some sense, this is not an intuitive definition, and you don't read this and be like, yes, privacy. But of course, if you ruminate it for a while, then you realize, yes, I guess this definition does imply things that feel like privacy to me. So we're going to kind of do those mental exercises together. So let's first think about the kind of a worst case nature of this, which you might want in a privacy guarantee. So you really don't want a conditional privacy guarantee. You don't want your privacy if Bob says yes and I have exactly 10 people in my database and so on. But you want privacy absolutely. And so that's kind of a worst case notion that it gives. And so in fact it is a worst case over all pairs of neighboring databases, which includes everyone else's data that kind of might exist in the whole world. No matter what they do, privacy holds. No matter what data you have, privacy still holds. And then also, no matter what you might want to pretend that your data are, privacy still holds. And so this is like a very, very nice strength of the privacy definition, is it is kind of like unconditional in terms of the input. The databases coming from you and from the entire rest of the world. Additionally, it is worst case overall bad things that you might be afraid of happening. Whether it's your insurance prices rising, I realize that's a very American worry because of course y'all have free healthcare. That sounds great, but we don't. The big scam. I forgot this being recorded. Oops, sorry. So it might be your health insurance prices rising. It might be journalists coming to your door asking about your search history. And I'm saying no matter what you are worried about happening, if it wasn't going to happen without your data, then it still will not happen with your data. And alternatively, if it does happen, for example, if I find a link between smoking and lung cancer, then I'm saying I would have learned this even if I hadn't seen your data because of this privacy. So basically, if it is a global property, I can learn it, but then I also would have learned it without you. But if it is something very specific to you, for example, search history, then it won't happen, except with some very, very small problem. So let's think about these privacy parameters. So we have this bound e to the power epsilon, and so I very high tech plotted epsilon e to the epsilon here, and so this goes from 0 to 6, and it goes from 0 up to 200 and something. So it gets big really fast, and it starts out very small. So we definitely want our epsilons to be small, somewhere in this space, so that we're getting a meaningful privacy guarantee, because over here this is not a particularly good bound if it's bound by a factor of 300. So let's kind of think about these extremes. On the one hand, if I set epsilon equals 0, then I'm having this term, and then my factor equals 1. And so this gives me perfect privacy. Why is that? Because in that case, I have to have this hold with equality, because I have to have inequality in both directions with a factor of 1. So this tells me everything has to happen with exactly the same probability, regardless of my data. So this is perfect privacy, but is in fact no learning, because it means that my output has to be independent of my data. This is not good, but this is a 1 extreme. At the other extreme, I can have epsilon equals infinity, in which case my bound is going to be infinity, and I'm going to have this bound here, and that is not going to bind at all. So this is not a real is kind of not a real constraint. And in fact, anything that is non-private, we can say that is epsilon equals infinity private. If I take your entire search history and your face and I post it on the Google homepage, that is going to be infinity private. So these are the two extremes, and we obviously would like to be somewhere in the middle so that we can get both good learning and good privacy. And in general, a thing to kind of keep in mind is that smaller epsilons are going to give you stronger privacy guarantees, because you'll be closer to this And so now there is this kind of like, million-dollar question: what is like the right value to choose? It should be something strictly positive and finite, but that's not particularly helpful. And I actually didn't even feel comfortable putting it on my slides as some like numerical guidance. I'll say it out loud. I guess it is being recorded, but really like isn't in writing. There's a long like historical debate about the appropriate epsilon values. In theory, back before like companies use this, everyone thought epsilon should be really small, something like 0.001. Or maybe something like diminishing in the size of your database, 1 over n, 1 over square root n. And this like worked fine in theory. There were some constants that were rather large, but it was fine. And then as people started to kind of like use this in practice, they saw, well, that's like too small, and it's like too close to 0, and I'm too close to like this bad case where I can't really do anything. And so then in practice, people tend to use like 1, 2, 8. If you use anything bigger than 10, reviewers are going to complain. There was one point Apple was like alleged to use 42, and there's like a Wired article about it, about how it's so bad. But like there's still no real answer. And in fact, this is a question I personally work on, and so I feel very comfortable saying like we don't know. Some people have a lot of feelings, but there's not a like concrete, scientifically founded answer. But like you can think of it as around 1, and like sometimes bigger, sometimes smaller. The reason why we like it to be 1 or smaller in theory is so then we can use a like Taylor expansion, and we can then like plug in this term as just being 1 plus epsilon, and then we get this, and then like a lot of our math becomes that is not a valid reason to use a particular epsilon value, but it is true. The kind of like historically, before this started being used in practice, all of our theorems assumed this because we thought epsilon equals 0.001, and why would anyone ever use a thing bigger than 1? And so this was a like reasonable assumption. These days, it's not so much, and there's some kind of like annoying but important work to be done in terms of like extending theorems beyond this case, because we're now seeing bigger epsilons and our theorems don't hold, and like they should, but like the math isn't. So that's also a like important but not very spicy research question. So that was about epsilon, and that is sort of like the main one, and that's a kind of like big parameter. People talk about epsilon, and they don't talk about delta very much. It's like a minor player in this game, but it is important, and it gives like a small slack in the privacy guarantee. And so like, why might you want that? So this should be a build slide, only for the top part for now. So why do we need delta to be positive? Well, for example, if I have different support under different databases, for example, if I have like 2 different neighboring databases, and there's some output that occurs with like positive probability under one, and with like 0 probability under the other, then I have this bound where like this is a positive number and has to be less than 0, and this can't happen, and then like everything breaks. So maybe it's nice if we have a little bit of like additive slack over here, so that we don't have like an impossible thing. So it's nice to have like a positive delta. A lot of the times, delta in fact will be 0, and that's why people tend to focus on the epsilon. You might still want a positive delta, even if you do have kind of like uniform support on all inputs. I think we'll see it as we talk about Gaussians. There's like tail-bound properties of Gaussians that make you have to have a delta, but it can be small, and so it's fine. And you can think of delta as allowing for a very rare failure of this epsilon dp here. And the failure can occur with a delta probability. However, it's very important when I say that what the probability is over and what are the conditionals, because it isn't just with some probability delta things fail, but in fact there's a lot of conditionals there. So in fact it's not true that it can fail on delta fraction of the inputs, but rather we're saying over the randomness inside of the algorithm, in the worst case over inputs, and then also in the worst case over output, there is a delta probability of the randomness and the algorithm causing failure. So it's a little bit more nuanced. When you say it in plain English without math, then you can say there's a delta chance of it failing, but in translating that into math, you have to be careful about kind of a delta chance over what. Okay, so it's nice if we have a small positive delta. How small should delta be? Well, we have a bad case. If I have delta equals 1, then I'm back to having no privacy whatsoever, because this is a additive slack on a probability. So if I allow +1 positive slack, then I again don't really have a kind of meaningful constraint. So we'd like delta to be small. And how small? Well, so let's consider the following example. Delta equals 1 over n, epsilon equals 0. And recall this means I am supposed to get perfect privacy. Okay? So I'm going to pick a person uniformly at random and publish all of their data in the clear. So this is going to be 0, 1 over n dp. And you can do some math to show it. How I basically have this 1 over n slack term. And this seems bad and should not be allowed. Oh, good. There's an exact quote. It is bad and should not be allowed. And so we shouldn't say delta equals 1 over n is fine, because it's not fine, because it allows you to do this under the presumption of a perfect privacy, but you're saying I'm going to violate someone's privacy dramatically with probability 1. So that's not good. So in fact, we actually want delta to be really small. It should definitely be smaller than is allowed here. And ideally, you want it to be exponentially small, cryptographically small, because you basically shouldn't be allowed to cheat on privacy via delta. And so if you have very, very small delta, then you can't do anything meaningful, but it just allows you to avoid probability 0. So this is kind of the right size of a delta. In your papers, 10 to the minus 5, depending on the size of your database. If you have a big database, 10 to the minus 6 or 7 or 8. But it should be something very small. Any more questions on? Yes. That is an excellent question. In case the mic didn't get it, it was kind of why do we have this particular distance notion over these two the distributions? Why do we have this thing? And that's a good question. And I think that anyone who tells you differential privacy is for sure the right answer is lying either to you or to like themselves. But I think the true answer is that it's pretty good and has a lot of the properties that we want, and we will continue to see more of those properties. And so it has nice properties that we would like a privacy guarantee to have. And people have been thinking about it for the past 15 years, and no one came up with a better one. No one found a fundamental flaw in it. And at this point we have a growing open source library of tools that will meet this privacy definition. And so that's not to say this is the right one full stop, but rather it's to say people have been working on this for a long time, long-ish in some scale, and they haven't found anything better. Maybe they will someday, in which case we'll all switch. But we don't have anything better, and we haven't in the entire history of this time, so it seems pretty good. Which I think is a more honest answer than saying it's perfect for all of these reasons. Because actually saying it's good for a lot of reasons, and we haven't found anything wrong with it, and we haven't found a better version. Any more questions? Okay, so in fact, I do want to talk about the importance of kind of a randomizing into a DP algorithm. Every DP algorithm that has non-trivial privacy parameters, meaning we don't have epsilon equals infinity, delta equals 1, any kind of a non-trivial any kind of a non-trivial DP algorithm is going to be randomized. And this is very important, and I want to sort of point out why it is. Imagine a case where I had some kind of a non-random algorithm, and on some database D, it would output S. And because it is non-trivial, it's going to output a different answer on some different input. Otherwise, it's doing a problem. Okay, and so then I have, sorry. And so for this S, I'm going to output S with a probability 1, and then for kind of all R's not equal to S, I'm going to output them with a probability 0. And so because this is I'm actually building in the opposite direction. Okay. And so this means all the other neighbors of D have to output the same thing, right? And so they have to output R with a probability 0, meaning they must also output S with a probability 1. And so on for their neighbors and their neighbors and their neighbors. And so this tells me all possible databases have to output S with a probability 1 if it's not random. So basically, if it's not random, then I have to output a constant function. And this is approximately true if you have a delta, how you can't output any R with a probability greater than delta. But as we're thinking of having delta exponentially small, you're basically approximately doing this. Yeah. Yeah. So if you somehow think that you're randomizing but you fail to, then you are not giving the privacy guarantee that you do. Yeah. And so then also as we kind of move into these private algorithms after the break, we will see that the really the crux of what is interesting algorithmically is kind of asking, where does the randomization come in, and what type of randomness, and what is the distribution, and where is it added? And so that is kind of like at the core of doing any kind of like a differential private algorithm design, is really thinking about like, where do I add noise and at what type? Okay, so click on some nice properties, and these kind of address the point before. Why do we think like, differential privacy is a good definition? Well, it has the properties in the following few. And the first one is that like it is robust to like a post process, meaning that if I take something that is an output of a differential private algorithm and I apply any function to it, then kind of like the result is going to maintain the same privacy guarantee. And so you can think of F as being some adversary. And so this is some adversary who's going to like, take your output that is published, and it's going to like try and break it. And we say, in fact, they can't, and they're going to maintain the same privacy guarantee regardless of the like, computational power of the adversary, if it's randomized, if it's not, if it's like unbounded computationally, if it's bounded, if it like has access to some kind of like outside information or not. Regardless of the adversary, it cannot break this privacy guarantee. And so this is like, definitely a property that you want privacy to have, is you want it to be like not broken by some adversary. One more thing that is very nice. Oh yeah. Mm-hmm. 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 You can. Yeah. Yeah. So it's like pretty strong. And one more property is that the privacy parameters compose as we perform more and more computations on the same database. Alternatively, kind of like a privacy parameters are going to degrade gracefully as I perform more and more computations. And so this version is the one that is kind of easiest to state, but is not the most tight. And it says if I have k different algorithms, each of them being an epsilon delta differentially private, and if I were to just run them all on the same database over and over again, that would give me k epsilon, k delta, d. And so this is very, very nice because it says if I want to build some complicated machine learning algorithm, I want to do deep learning and train over bunches of rounds. All I have to do is I have to count up how often did it access my data through some a differential private algorithm, and it was k times. Each of them were epsilon delta dp. I now then immediately know the privacy guarantee of my overall algorithm without having to go through line by line analytically checking. But in fact, I have this guarantee. And if you have a different epsilons, you can just take their sum. It's okay if they're different values. Epsilons and deltas can just add up. It's very simple. If you want a version of it that is more tight, you get something like this that is a little bit weirder looking, but it basically gives you, instead of k times epsilon, you now get square root k times epsilon, but you have some other weird log terms and some lower order terms. One more thing here is that you can also choose these things adaptive. And so before I said here's my k algorithms, I'm going to run them one by one, and then I will be done. And so this is like, what fraction of my database are men? What fraction of my database have like diabetes? Whereas here, maybe I want to first do some kind of like model selection. And then kind of like based on the output of that algorithm, I want to train a model using the one that I chose. And so in fact, I can use like previous outputs as an input into my new algorithm, and that's still fine, and we can still maintain the same privacy guarantee. And so effectively here, you are getting hey, like better epsilon at the cost of a worse delta. And so you're like, delta is going to be larger by some small term because our deltas are small, and so it's fine. And you're getting, hey, like, better, like, asymptotically, although perhaps worse than the constant epsilon. And so if you have like appropriate constant, then you actually do want to use this one. And I will mention it is in fact a kind of like open research question of kind of like how to find like a tighter privacy composition guarantees under like a specific assumption. Already we have a totally different privacy guarantee if you're doing like a deep learning with adding Gaussian noise. We have a different, tighter, better composition result there, but it's like only like under those like assumptions in that case. But of course, if you're doing deep learning, it's fine. And so this is like an open question. We are getting like better like composition tools every like couple of years, and it's not clear that we're done yet. And so I think this is a like an interesting question. And then finally, we have like a group privacy, and this is important because we have like phrased everything so far in terms of like a privacy of the individuals, and we're saying like you change your data and it won't learn about you. But what if like you appear twice in a database? Do you lose all of your privacy guarantees? What if like you exist in like a database and your family does too, and your data happen to be correlated? Do you lose all privacy? And the answer is in fact no, but rather you're like privacy guarantee like depends on the group size. And so recall we said differential privacy allows you to learn about the population, but still kind of like not about the individuals. And so of course if you get like a larger and larger group size of something of like order n, order like square root n, of course we can learn about the population, but that's because you cease to become a kind of like an individual at that point, and you instead become a population yourself. And so formally we say that if like that if I have two like data sets and they differ in k entries, and I run like epsilon delta dp algorithm, I'm going to have this guarantee on the outputs. Again, I'm going to effectively lose a factor of k in both parameters. And so alternatively, this can say similar data sets are going to receive similar outputs, where like similar is basically k. And this is in fact very helpful as we're talking about like a generalization in machine learning, and we'll talk about this a different day this week, because if I'm going to learn on a sample, what I'm actually trying to do is I'm trying to learn on some other like hypothetical sample that it could have drawn from the same underlying distribution. And so if things are like well behaved, these are going to be similar. And so then I can say that say in fact there's a tie between like differentially privately learning on a sample and also the kind of accuracy guarantees you might get if you learned on a fresh sample instead. And we'll see this in a more formal version. So just to kind of wrap up things that we have been saying about like a differential privacy, I like this picture. Think of like curves with a slight shift. And we know that it has like very nice properties that allow for like modular algorithm design. And this is why we're going to see very, very simple building blocks after the break. And they're going to be almost like stupidly simple algorithms, but they're in fact very powerful because they can be used in this kind of modular way to build much more like complicated learning things. We have these like very strong worst case guarantees, and we also have these like privacy parameters that allow us to move smoothly in between like 0 to infinity in our privacy world. And then again, in practice, we have this kind of like diverse algorithmic toolkit, which I haven't talked about at all, like it exists, which is basically in the past like 15 years, computer science researchers have been building algorithms, building code, deploying things in practice, and these are like used in practice. And this is like a very, very small sample. Apple, Google, Uber, U.S. Census Bureau, Microsoft, Facebook, Snapchat. Most of the major tech firms do it, and also a lot of the kind of like smaller ones. Yeah. That is a good question. They, for the most part, do it on things that don't affect revenue streams. Which I think that's how we'll know differential privacy made it, is when they start using it on things like advertising. Like for example, Google used it on like a Chrome, like a crash reports. And so if Chrome crashes, they want to know what was your website, what were you doing, what type of like plugins and so on. But they don't like want to store all that information about you. They actually want to find out what are the like top 10 domains that like crash Chrome the most. And so they use like a differential privacy there. Right now, Apple actually uses it a lot, but in some sense, they have a different revenue model because, like, really at their core, they're a hardware company, and so if they can have like privacy built into their software, then they can sell more hardware. And so, in some sense, they're a leader because they like aren't actually a like data firm, but in fact, they are kind of a hardware firm. Yeah, there's great like a controversy surrounding this one that I will not talk about while I'm being recorded, but I will happily talk about later. Any more questions? Back. Yeah. That is an excellent question. And it was asking about like, about 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 kind of like privacy and also kind of usability of the data. And I'll mention this is like at the core of this debate because you obviously want both when you're like collecting citizens' data, publishing government statistics, making important government decisions. You want privacy, and you also want to make sure that you're publishing like accurate things and you're making data usable. But in kind of like at a high level, what we'll talk about like 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 the entire rest of my talk talks is about how to achieve both, because in fact it's really easy to achieve one of these without the other. I can achieve perfect privacy by just like throwing away data and and like outputting garbage, but that's like not very helpful. And so really good like a private algorithm design is going to be about how can I enable accurate analysis of my particular task and still ensure differential privacy. And there are in fact lower bounds of what is impossible that will trade off epsilon sample size and your kind of like an accuracy metric for like a particular task. But in some sense, this is what makes like a differential privacy exciting, is that it sounds like too good to be useful. And in fact, it is very, very useful to the point where there's like no companies using it. I think if we can improve on this like accuracy bit a little bit, then you might see it in like ads, hopefully someday. But at this point, even if it's like 1% loss and like revenue, companies don't like that. Yeah. Yeah, so this is a really good question, and maybe I will talk about it this week. Maybe I won't. I haven't actually planned everything, but I think this is like a really really big question, which is kind of like how do you communicate it? And so let's say you're a company and you decided I'm going to use like a differential privacy because I saw this like talk in France and I'm convinced it's the best ever. How do I like tell my lawyers? How do I tell my users? Like, how do I like, do a PR press release? And this is also something that I'm like very actively working on. And so there isn't a good answer now. Right now, each company does it in a different way. And like, some of them are doing it in a better way and some of them are doing it in a less better way. But I think this is something that we like don't really have standards yet in terms of like how do you communicate effectively like what you are doing. Even if you're doing things well, how do you like communicate that without having to give a like multi-hour mathematics of machine learning talk to somebody's like grandma who like lives in a village. So I think with that I will break the first hour and we'll come back and we'll talk about some of the algorithms to achieve this.